Welcome! In this session, we'll dive into a coding problem titled Replace the Substring for Balanced String. Together, we'll explore the problem, break it down step by step, and review different approaches to solve it. Let's get started. In this problem, you are given a string S of length n, where n is a multiple of 4, and the string consists only of the characters Q, W, E, and R. A string is considered balanced if each character appears exactly n/4 times. Your task is to determine the minimum length of a substring that can be replaced with any other string of the same length to make S balanced. For the input, you are given a single string S containing only the allowed characters, and the output is an integer representing the minimum length of the substring that needs to be replaced. Let's look at some examples to understand this better. In the first example, the input string is S equals QWER. The output here is 0. This is because the string is already balanced. Each of the characters Q, W, E, and R appears exactly once, which matches the required count of n/4. Since no substring needs to be replaced, the minimum length is 0. Now, in the second example, the input string is S equals QQWE. Here, the output is 1. To understand why, let's examine the character frequencies in this string. In the string S equals QQWE, the counts of the characters are as follows: Q appears 2 times, while W and E each appear once. The target count for each character, calculated as n/4, is 1. To balance the string, we need to reduce the count of Q to 1. This can be achieved by replacing one of the Q characters with either W or E. For instance, replacing the first Q with W results in the balanced string QWWE. Therefore, the minimum length of the substring to replace is 1. Let's move to the next example to explore a case where multiple characters need to be replaced. In the next example, the input string is S equals QQQW. Here, the counts of the characters are Q appears 3 times, and W appears once. The target count for each character remains n/4 equals 1. To balance the string, we need to reduce the count of Q from 3 to 1. This requires replacing any 2 Q characters with the other characters E and R. For example, replacing the first 2 Q characters with E and R transforms the string into ERQW, which is balanced. Hence, the minimum length of the substring to replace is 2. Now, let's consider some additional edge cases to better understand how the solution applies to different scenarios. Consider the edge case where the input string is S equals QQQQ. Here, all 4 characters are Q, and to balance the string, 3 of these Q characters must be replaced with W, E, and R, respectively. This makes the minimum length of the substring to replace 3. Another edge case is S equals WERR. This string is nearly balanced, but one R needs to be replaced with Q to achieve balance. In this case, the minimum length of the substring to replace is 1. These examples highlight how the problem can be approached for strings of varying imbalance levels. To begin solving this problem, we can consider the brute force approach. This method involves checking every possible substring of the string S. For each of these substrings, we replace it with the required characters needed to balance the string, and then check if the resulting string satisfies the condition of being balanced. A balanced string means that each of the 4 characters, Q, W, E, and R, must appear exactly n/4 times, where n is the length of the string. The intuition behind this approach is straightforward. Since any substring could potentially be the one we need to replace, we systematically explore all possibilities, calculating the replacement cost and verifying balance for each one. However, this comes at a significant computational cost. The time complexity is O(n) cubed, as checking all possible substrings takes O(n) squared, and verifying balance for each substring adds an additional O(n). Despite requiring no extra space, making it O(1) in terms of space complexity, this approach is impractical for larger input sizes due to its inefficiency. With n being a multiple of 4, this method quickly becomes computationally expensive, highlighting the need for a more optimized solution. Now, a more efficient solution leverages the sliding window technique. This approach identifies the smallest substring that can be replaced to make the string balanced. The first step is to calculate the frequency of each character in the string S and determine the excess count for each character. This is how many times a character exceeds the target n/4. Using 2 pointers, we create a sliding window that dynamically adjusts its size. The goal is to ensure that the substring outside the window balances the string. This means that if the substring inside the window were replaced, the remaining characters would meet the balance criteria. The intuition here is that rather than checking all substrings, we can focus on finding the minimal substring whose replacement resolves the imbalance. The algorithm begins by calculating the frequency of each character and the excess counts. Then, the right pointer expands the window while ensuring the substring outside the window is valid. As soon as this condition is satisfied, the left pointer shrinks the window to find the smallest possible substring. Finally, the algorithm returns the length of this minimum window, ensuring an efficient solution. The sliding window approach is highly efficient, with a time complexity of O(n), since both the left and right pointers traverse the string only once. Additionally, it has a space complexity of O(1), as it uses only a constant amount of extra space for the frequency map. An alternative approach combines binary search with the sliding window method. Here, binary search is used to find the smallest possible window size, and the sliding window verifies the feasibility of each candidate window size. The intuition behind this hybrid method is that binary search narrows down the potential window sizes, while the sliding window efficiently checks if replacing a substring of that size balances the string. This combined approach has a time complexity of O(n) log n, as binary search requires O log n iterations, and each iteration involves a sliding window operation of O(n). The space complexity remains O(1). While this method is competitive in terms of performance, it introduces added complexity without significant benefits over the pure sliding window approach, making it less preferable for this problem. The sliding window approach emerges as the most suitable strategy for solving this problem. It is efficient, intuitive, and avoids the computational overhead of explicitly checking all substrings or combining binary search with sliding window. By leveraging the idea of excess counts and dynamically adjusting the window boundaries, this approach minimizes computations while ensuring correctness. There are 3 key observations that underpin this method. First, a string is balanced if all characters appear exactly n/4 times. Second, any character exceeding this count must have its occurrences reduced by replacing an appropriate substring. Third, the sliding window is a powerful tool for identifying the smallest substring that satisfies this condition. While the brute force approach is simpler to implement, its high time complexity makes it impractical. The binary search approach, though competitive in performance, adds unnecessary complexity. Therefore, the sliding window approach, with its O(n) time complexity and O(1) space complexity, represents the optimal balance between simplicity and efficiency, making it the clear choice for this problem. To solve this problem, we need to determine the smallest substring in the string S that can be replaced to make the entire string balanced. A string is considered balanced when all 4 characters Q, W, E, and R appear the same number of times. The first step is to calculate the frequency of these characters in the string. Using these frequencies, we determine the ideal frequency for each character, which is simply the total length of the string divided by 4. If the character frequencies already match this ideal count, the string is already balanced, and the result is 0 since no replacement is required. However, if any character exceeds its ideal frequency, those excess characters will need to be reduced by replacing a substring. Identifying these excess characters is key to setting up the solution. Now, to find the smallest substring that can be replaced to balance the string, we use the sliding window technique. This approach involves maintaining a dynamic window within the string and adjusting its size to evaluate potential substrings. We begin by initializing 2 pointers, start and end, both set to the beginning of the string. The end pointer is expanded to include characters in the window, while the start pointer is adjusted to shrink the window when a valid substring is found. The condition we check is whether removing the characters within the current window results in the remaining string being balanced. If so, we record the window's size and attempt to shrink it further to find the minimum valid substring. By continuously adjusting the window and tracking the smallest size, we can efficiently identify the optimal solution. This sliding window approach is highly efficient for solving this problem. Instead of generating all possible substrings, which would be computationally expensive, we focus only on windows of interest, significantly reducing the number of substrings we evaluate. By tracking the frequencies of the excess characters, we simplify the problem to just ensuring no violation of the balance condition exists outside the current window. Additionally, the algorithm dynamically adjusts the window size, allowing us to optimize for the smallest substring early and avoid unnecessary computations. To implement this, we rely on a frequency dictionary to store character counts and two pointers to define the window boundaries. These tools ensure that the solution remains both time and space efficient. Analyzing the complexity of this approach, the time complexity is O(n). This is because the sliding window ensures that each character in the string is processed at most twice, once when the end pointer expands the window and once when the start pointer contracts it. The space complexity is O(1), since we only use a fixed number of variables and a frequency dictionary with at most 4 entries for the characters Q, W, E, and R. Regarding edge cases, the algorithm handles scenarios like an already balanced string, in which case the result is 0, and strings where all characters are identical, which would require replacing the entire string. Additionally, for strings shorter than 4 characters, the balance condition is inherently unsatisfiable, making the input invalid. Let's walk through an example to clarify how this algorithm works. The input string is Wekkerk. First, we calculate the initial frequencies. Q appears 3 times, W appears 3 times, E appears twice, and R appears once. The ideal frequency for balance is the total length, 9, divided by 4, which is 2.25, rounded down to 2 for all characters. From this, we identify that Q and W exceed the ideal frequency, each by 1. Using the sliding window technique, we start with both pointers at the beginning of the string and expand the window while adjusting the frequencies. When the characters in the window are removed and the remaining string is balanced, we shrink the window to find the smallest valid substring. For this example, the minimum substring length is 4, and valid substrings include WWEQ or QERQ. The result is 4. This solution tackles the problem of finding the smallest substring in S that, when replaced, makes the string balanced. A string is balanced if each of the characters Q, W, E, and R appears exactly in ////4 times, where n is the length of the string. The implementation first uses the counter class to count the frequencies of each character in the string. It calculates the target frequency for each character, which is n/4. If all characters are already balanced, frequencies are less than or equal to the target, the function immediately returns 0 as no replacement is needed. Next, the function uses the sliding window technique to find the minimum substring that can be replaced. The right pointer expands the window by iterating through the string, while the left pointer shrinks the window to maintain the balance condition. The count dictionary is updated dynamically as the window changes. The inner while loop ensures that the substring currently defined by the window satisfies the balance condition. Each character's frequency is less than or equal to the target. During this process, the function calculates the length of the substring and updates the minimum length found so far, min_len. Finally, the function returns min_len, which is the length of the smallest substring that can be replaced to balance the string. This approach has a time complexity of O(n), as both pointers traverse the string linearly, and a space complexity of O(1), since the count dictionary has a fixed size of 4. Here, we start by importing the necessary libraries and defining a class-named solution with a method called balanceString. The goal of this method is to determine the minimum length of a substring that can be replaced to make the given string S balanced. A balanced string is defined as one where each character Q, W, E, and R appears exactly n/4 times, where n is the length of the string. We calculate this target by dividing the length of the string by 4. Next, we create a hash map to count the frequency of each character in the string. We iterate over the string, updating the count for each character. After populating the map, we check if the string is already balanced using a helper method named isBalanced. If it is, we can directly return 0 since no replacement is needed. If not, we initialize 2 variables, left to represent the start of the sliding window and minlen to store the minimum length of the substring we need to replace. Then, we begin iterating over the string with a right pointer, which represents the end of the sliding window. For each character at the right pointer, we decrement its count in the map to simulate including it in the window. Now, within the loop, we continuously check if the current window is balanced by calling the isBalanced method. If it is, we calculate the length of the window using right left plus 1 and update minlen to the smaller value between the current minlen and the window length. Next, we increment the count of the character at the left pointer to simulate removing it from the window, and then move the left pointer one step forward. This process continues until the window is no longer balanced or the loop ends. Finally, we return minlen, which represents the minimum length of the substring that needs to be replaced to balance the string. The helper method isBalance takes the character count map and the target value as inputs. It ensures that the frequency of each character Q, W, E, and R in the current window is less than or equal to the target. If all conditions are satisfied, the window is balanced, and the method returns true, otherwise, it returns false. To solve this problem, we start by determining the target frequency for each character in the balanced string. Since the string length is 8, dividing it by 4 gives us a target of 2 for each character. Using the counter function, we calculate the initial frequencies of the characters in the string, which are W2, Q4, R1, E1. Clearly, the string is not balanced because the character Q appears more than the target, while R and E appear less. To address this, we use the sliding window technique. We initialize the left pointer at 0 and the min_len variable to the length of the string, which is 8. The sliding window process begins by moving the right pointer step by step. At the first step, when right is 0, the character W is encountered. We decrement the count of W by 1, resulting in W1, Q4, R1, E1. However, the string remains unbalanced because Q still exceeds the target frequency. At the next step, when right is 1, the character Q is encountered. We reduce its count, resulting in W1, Q3, R1, E1. The string is still unbalanced. Then, as right moves to 2, the character W is processed, reducing its count to 0 and updating the frequency dictionary to W0, Q3, R1, E1. The string remains unbalanced. Next, at right equal to 3, the character R is encountered, and its count becomes 0, leading to W0, Q3, R0, E1. The string is still not balanced. Finally, at right equal to 4, the character Q is processed, reducing its count to 2 and updating the dictionary to W0, Q2, R0, E1. At this point, the string becomes balanced because all characters meet or fall below the target frequency. We then attempt to shrink the window size by incrementing the left pointer. When left is incremented to 1, the count of W is restored, resulting in W1, Q2, R0, E1. The minimum window length is updated to 4. While the loop continues further, no smaller window is found, and the minimal length remains 4. Thus, the function returns 4. In this next example, we consider the string s equals QQWE. The length of the string is 4, so the target frequency for each character is 1. Using counter, the initial character frequencies are calculated as Q2, W1, E1. The string is unbalanced because Q exceeds the target. Using the sliding window method, we initialize left at 0 and min_len at 4. When right is 0, the character Q is processed, reducing its count to 1 and updating the dictionary to Q1, W1, E1. The string becomes balanced at this point, so we attempt to shrink the window. Incrementing left to 1 restores the count of Q to 2, resulting in Q2, W1, E1. The minimum length is updated to 1, which is the smallest possible value. As the sliding window loop completes, no smaller window is found, and the function returns a minimal length of 1. In the final example, we analyze the string s equals QWER. The string length is 4, so the target frequency for each character is 1. Using counter, we find that the initial frequencies are Q1, W1, E1, R1. Since the string already meets the target frequencies for all characters, it is balanced from the start. Thus, the function immediately returns 0, as no replacement is required. To summarize, the sliding window technique is an efficient method for identifying the smallest substring that can be replaced to achieve balance. The count dictionary plays a crucial role in dynamically tracking character frequencies as the window expands and shrinks. Across the examples, we saw cases involving strings that were already balanced, required minimal replacements, and required larger replacements, illustrating the versatility of this approach. The time complexity of the sliding window approach can be broken down step by step. First, we initialize the counter to calculate the frequency of each character in the string S. This operation iterates over the entire string, which takes n time, where n is the length of the string. Next, the outer loop, which uses the right pointer to traverse through the string, also requires n time since it iterates once from the start to the end of the string. Additionally, there is an inner while loop that adjusts the left pointer to shrink the window when necessary. While it might seem like this adds extra complexity, the left pointer only moves forward and never backtracks, meaning it traverses the string at most once. This ensures that the inner while loop contributes an amortized n time complexity overall. Combining these elements, the total time complexity of the algorithm is n for the initialization, n for the outer loop, and n for the inner loop, resulting in an overall time complexity of n. Now, let's examine the balance condition check and how it impacts time complexity. The operation all count C equals target for C in QWER ensures that each character meets the target frequency condition. Since there are only 4 characters in QWER, this check runs in constant time, or 1, for each call. This operation is performed inside the while loop and also in the if condition outside the loop, meaning it is executed n times in total, contributing n to the overall time complexity. Combining all these steps, the total time complexity remains n. Shifting to space complexity, the counter object is used to store the frequency of the 4 characters. Since the problem is limited to just these 4 characters, the space required here is constant, or 1. Similarly, additional variables such as left, right, min_len, and target also require constant space. Thus, the space complexity is 1. The input string S itself does not contribute additional space beyond what is already provided, as it is simply passed as an argument to the function. This means the total space complexity is still 1. To highlight the efficiency of the sliding window approach, let's compare it to a brute force solution. A naive approach would involve generating all possible substrings, checking their length, and verifying whether replacing the substring leads to a balanced string. This would require n squared time for generating substrings and n time for checking each one, leading to an overall time complexity of n cubed. Space complexity for the brute force approach would be 1, excluding the input storage. In contrast, the sliding window approach avoids redundant substring checks by dynamically adjusting the window size, which reduces the time complexity to n. The space complexity remains 1, making the sliding window solution far more optimal in both time and space. Finally, let's analyze the algorithm under best, average, and worst case scenarios. In the best case, the input string S is already balanced. Here, the condition all count C equals target for C in QWER is satisfied immediately, and the algorithm terminates after the initialization step, taking only n time. In the average case, the sliding window dynamically adjusts for a mix of balanced and unbalanced substrings. The amortized time complexity remains n, since the left and right pointers still traverse the string linearly. Even in the worst case, where the string is highly unbalanced, the while loop needs to shrink the window for nearly every iteration of the right pointer. However, the left pointer only traverses the string once, ensuring that the total time complexity does not exceed n. Across all scenarios, the sliding window approach guarantees linear time complexity, making it a highly efficient solution for this problem. When tackling this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to significant issues. Examples include handling empty strings, strings that consist of identical characters, or very short strings. Overlooking these can result in runtime errors or incorrect outputs, as the program may not account for such scenarios. Next, relying on inefficient brute force methods is another pitfall. While brute force can help with understanding the problem initially, it often fails for large inputs due to time constraints, making it unsuitable for interviews or competitive programming. Another frequent issue arises with sliding window techniques. It's easy to forget to properly adjust the window size based on problem constraints, which can compromise the logic and lead to incorrect results. Lastly, there's the notorious off-by-one error. Miscalculating indices, whether when iterating or slicing strings, can create subtle bugs, leading to invalid substrings or out-of-bound errors. By being mindful of these mistakes, you can avoid common traps and build more robust solutions. Overcomplicating the problem is another mistake to guard against. Sometimes, beginners add unnecessary data structures or over-engineer their approach when a simpler solution would suffice. This only increases complexity, wastes time, and makes debugging more challenging. To excel in interviews, it's crucial to master sliding window techniques. Many problems involving substrings or balancing rely on this approach, so you should be able to explain why it's optimal and how it improves upon brute force. Additionally, interviewers often test your ability to reduce space complexity. Be prepared to weigh the trade-offs between time and space in your solution. Recognizing patterns is equally important. Problems involving balancing, counting, or prefix sums are common in substring-related questions. Lastly, always test edge cases thoroughly. Strings of length 0, 1, or the maximum allowed length should always be a part of your test plan. This shows attention to detail and ensures your solution is robust under all conditions. This problem shares similarities with several related problems that you may encounter. For instance, LeetCode 3 focuses on finding the longest substring without repeating characters, while LeetCode 76 looks at finding the minimum window substring. Similarly, LeetCode 1248 involves counting the number of nice subarrays, and LeetCode 424 challenges you to identify the longest repeating character replacement. Each of these problems reinforces key techniques like sliding windows and efficient counting. When exploring alternative approaches, brute force is often the simplest to implement, but its performance is usually poor, with time complexities as high as n cubed, in some cases. It's best suited for small inputs or as a way to validate more optimized solutions. On the other hand, the sliding window approach is far more efficient with a time complexity of n. However, it demands careful implementation to ensure the window expands and contracts appropriately based on the problem's constraints. Choosing the right approach depends on your input size and the complexity of the problem. In addition to sliding windows, the two-pointer technique is another powerful tool for solving these types of problems. While it shares similarities with sliding window, it can be less intuitive for beginners. This technique works well when problems involve maintaining balances or ranges between two constraints. Another approach involves using a hash map or a frequency array. This is especially useful for counting characters or tracking occurrences efficiently. The trade-off here is increased space complexity, which can be n for general cases or reduced to 26 when working with alphabets. Understanding when to use these techniques is critical. For example, two-pointers are great for problems dealing with ranges, while a frequency array is ideal for scenarios where you need quick lookups or updates. By mastering these methods and knowing their trade-offs, you can adapt to a wide variety of problems and optimize your solutions effectively. Great job following along. We reviewed the problem, analyzed the brute force approach, and highlighted key takeaways. Keep practicing to refine your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!